Thank you very much, friends. We have our third speaker, Dr. Andrea Carminati. He is professor of soil hydrology at the University of Goettingen, Germany. Dr. Andrea, please.
Yes, so you're many, eh? It's big here. So, hello everybody. My name is Andrea Carminati. I think this should work. Yes. Okay. So the content of this talk. So the objective of this talk is to discuss the principle of how water flows from the soil to the roots, in particular when the soil is getting dry and the transpiration rate is high, which is mainly when you have drought. So basically, it's the case that we are addressing in this conference. And to solve this general question, I'm posing here three more specific scientific questions that we should address, still pretty general. So the first is, so how easy is to extract the water from the soil? So means, what is the water potential that the plants need to get the water out of the soil? And this, we also need to think about fluxes, so we need to sustain a flux. This we'll see later. The second question is something that is the objective for many of you, is what root properties, so what root properties are needed to facilitate or eventually limit the fluxes of water into the plants. And often you talk about deep roots, dense root distribution, but maybe there is more. Many roots are different. They have different traits. They have different anatomy, different hydraulics, which we will see later today. And the third question is a bit also my question. You know, I'm a soil hydrologist, a soil physicist, and I'm questioning myself, okay, what is my job here? So what can I bring you? So to what extent soil physics or research in soil physics may advance the research on drought? So let's see if I can make this. So, and to address this question, it's important in my view to consider the water flow rates. So plants, roots need to take up a given amount of water, but it's not only this. They need to take up water fast enough to match with the water loss from the leaves. This is pretty trivial, but I think it's a critical point. So we need to think about fluxes, and I think a more precise question about roots is what root traits allow to sustain high water flow rates. And I will anticipate a little, so the conclusion of my talk, so in case if I'm late, I make the conclusion. So one of the main conclusions will be that biophysical processes that happen at a very small scale in the vicinity of the root surface, and we're talking about the first millimeter around the roots, where you have root hairs, where you have root exudates, where you have a lot of microbial activity. So this small region, the biophysical processes happening there, they're very crucial to allow to sustain high transpiration rates, or eventually to limit the fluxes there. And if we want to address this point, we will need to study the process at a very high spatial and temporal resolution. So we need to look at minutes, and we need to look at millimeters, which is a very different scales compared to what we observed so far. But I believe it's still relevant, and I will hope to convince you about that. So let me start with general principles of how plants take up water from the soil, how water moves through the system. So transpiration from the leaves generates a suction, a tension in the xylem of the plants. So it's a tension. We have a suction, and the suction that is required to move the water from the soil into the roots, it depends on several properties. It depends principally on the root hydraulic conductance depends on how much. So it depends on the conductivity of the whole plants, which in turn will depend on radial and axial conductivity of the roots, which probably we will see later today, and depends on the architecture of how the roots segments are arranged. And this we will see later in the talks by Treyer, by Tyerman, and Ahmed later on in the day. This is the first thing, so plants. And the second is also how water is moved from the soil. So mainly the soil water potential. So a brief definition of soil water potential is this is the work that you need to do to get the water out of the soil reversibly, isothermally, but means basically extracting the water from the soil. But when the plants, they also have to move it. So we will have a conductivity problem, and the conductivity of soil changes very much with the soil water potential. You may have a decrease of conductivity in soil that is 7, 8 orders of magnitude. So we're talking about something very variable. And you can summarize simply this concept with now a general equation that I put it here at the bottom that says that the water flow, so volume of water per time, they are equal to a conductance and a difference in water potential. The difference in water potential is what is driving the water. And the conductance, it tells you how easy water flows for a given water potential. Very general. So let's get a bit more quantitative. And let's look at this sketch. So this is a crop with a low VPD, so low transpiration rate. And we are looking at 2 points. And the water movement from a given point, oh, this one I have to use. A given point in the soil, this point A, and the point up here in the xylem, still in the plant. And we are looking at how much force, how much difference in water potential is needed for the plants to get the water out. And this is summarized in this part of the figure. So here you have the soil, a point in the soil. Here you have a given point in the xylem. And this imaginary line here, this represents the interface between the soil to the left and the right, and the plant to the right. Of course, there is nothing like this in a plant. So you have many interfaces and all with a different potential. This is just a simplification, but it allows to understand the picture. So what happens we start with a wet soil. And in a wet soil, the water potential is not very negative. So plants don't need big work to get the water out. And when the transpiration is low, you have almost no dissipation of water in the soil. So this line is almost straight, it's almost horizontal. Instead, in the plant, you have a loss of water potential, which is needed to drive the water to the point B. So always water flows from high to low water potential, and depending on the flow rate and the conductivity, this difference in water potential is big. So if you increase the transpiration rate, so in the soil, there's not much going on. The conductivity of the soil in wet soil is negligible. So you almost still don't get any gradients. Instead, in the plant, bigger fluxes, like in the question, bigger flow, so you need a bigger difference in water potential. And the leaf water potential will go down. When the soil gets dry, what happens? So let's still start with a low transpiration rate. So the water potential got negative, more negative. It's more difficult to get the water out of the soil. But still, you don't expect very big gradients in the soil. And in the plant, if nothing is changing, well, it may change, and we will probably discuss this, you expect similar gradients. But in dry soil and at high transpiration rates, things start to happen. So what will happen is that you will start to have big drop in water potential in the soil, which are almost similar to what you lose in the plant. So this is due to the fact that the soil processes are very nonlinear. And if you have high fluxes, you start to have bigger and bigger gradients until a point where the soil not easily can sustain the fluxes. So what it says here is that you may dissipate a lot of water potential to move water from the soil in some points to the root surface. What we don't know, the thing is that we don't know where this happens. So to assess these 3 points, so this is all the work that the plants need to get the water out of the soil, bring to the xylem at the given transpiration. And you may summarize with 3 works. First, make the water free from the soil. Second is this part, you need to have the water flowing in the soil. And the third part is how much water you lose to flow it in the plant. Now, which of these 3 elements is bigger, and how can we predict them? So in this talk, I will mainly look at this part because it's not very easy to predict, it's not very easy to model, and it's not very easy to measure it. So there are not very many measurements for this. And I will show one example later. And the main hypothesis of the work that I'm going to present you is that large drops in this water potential, actually they happen in this very small region, this tiny region around the roots. And let me explain this with a simple sketch. This is a single root extracting water from the soil. And these blue lines, they represent the gradients in water potential towards the roots. When the soil is wet, these gradients are almost horizontal. But as the soil gets dry, the gradients, they start to get steeper and steeper. Why do they get steeper? 2 very simple physical laws. One is geometry. So you have a radial flow, you have a convergent flow. So the closer you get to the root, the higher is the flow rate. And the higher is the flow rate means that the bigger they get the gradients. So the water is kind of accelerating close to the root. Just a radial problem. And of course, you have to think when the roots are thin, they have a small diameter, this problem is bigger. The second is the nature of soil properties, which are summarized in this equation here, where the flow is equal to a conductivity times a gradient in water potential. And since the water potential is decreasing toward the roots, the conductivity decreases toward the roots, and then this creates this kind of exponential. This thinks that the closer you are to the root, the steeper there are the gradients. Until you have a very critical point when basically the soil is getting dry, this number decreases, the conductivity goes down. To sustain the same flux, you need bigger gradients, but bigger gradients means that close to the root, the conductivity goes lower, and at the point, the system fails. And then you have a kind of hydraulic failure, and you can predict that there is a maximum flow rate that the soil can sustain. This is a soil problem. At this point, if either the leaves close the stomata and they do it and you reduce transpiration rate, or you cannot keep the mass balance and the roots start shrinking. And this is something that nowadays we can visualize. We can make, this is an X-ray cross-section of a plant exposed to a drying soil. And you see that this was a looping root. You have a root in the middle, surrounded by soil. And during this drying cycle, the roots lost contact to the soil. And here I colored in red the air-filled gaps between the root and the soil. And this creates an additional resistance to the flow. Now, the thing is that plants, roots, they know soil physics. Over the year, they learned this problem, this nonlinearity around the roots, and they found some clever and efficient strategies to cope with that, to fix this problem. So these gradients that I was showing you before, they happen in the first millimeter around the roots. This goes very much with the root radius. And now, if you change the properties of that region, you solve part of that problem. And they do it in 2 ways. So they do it by growing root hairs, which they extend the root radius, and they can capture the water from a bit far away. So you solve the radial problem. And they do exuding a particular material, mucilage, the gel exuded at the root tips, which keeps the region between the root hairs wet, and in this way conductive. And this was a picture from Margaret McCulley that shows a microscopic section of a root and the surrounding soil. And you can see, and many of you probably observed, when you dig the roots out of the soil, you see that some particles stay attached. This is what is called the rhizoshift. This is a very coherent layer of soil that is bound to the roots due to root hairs and mucilage that acts as a glue, and this keeps the root hydraulically and mechanically connected to the plant, to the soil. Now, so let's discuss a few words about the properties of mucilage. This is an example. This on the right, you see the nodal roots of a maize plant, and if you cover this with water for some time and you remove water, you see this gel surrounding the roots. This is the mucilage, and on the left side you see the mucilage at the microscope when it's fully expanded. It looks similarly to a sponge. You can imagine as a sponge. When you immerse it in water, it starts to swell and expand, and it can absorb up to 500 times its dry weight. So 1 milligram of gel may get to absorb 1 gram of water. And when you put this material in soil, okay, so when you put it in soil, the consequence is that the soil will hold more water at the given water potential. So this is a typical measurement of the water retention curve. It says on the x-axis how much water you have. On the y-axis, the water potential in the soil. Typically, it's a nonlinear curve. You start to apply the suction, you drain the soil. When you add to the soil, this is the red line, when you add to the soil mucilage, you get more water. So mucilage increases the capacity of soil to hold water. And this is an example how we started to look at this story. So this is a neutral radiography. So it's similar to X-ray, but you mainly see water. And so roots are made mainly of water. So you see the roots dark. It's the upper 5 centimeter of a lupin plant with the main root in the middle and some laterals with some cluster. The colors, they are proportional to the water content. So you see around the roots, you see more blue regions. So you see that even when plants transpire, around the roots, the soil is a bit wetter, which initially didn't make sense, but it's nothing strange. It's just that the properties of the soil is different. And the consequence of this mucilage, they can be visualized in this model. In this model, just a model so far, it's still an hypothesis, but we calculated the gradients of water potential around a single root during a drying experiment. And on the left, on the right side, it's without mucilage, and you predict that during drying period from day 0 to day 5, you start to get a big drop in water potential around the roots. And this is done at a given constant flow rate. And at this point, this blue line, the blue line refers to when the plant cannot anymore take up water at that rate. And you see again that these gradients in water potential, they happen in the very first millimeter. Now, in this case, I resimulated the story, having mucilage in the soil, so having the part close to the root, this region, impregnated with mucilage, and the consequence is that the gradients, they're not anymore so steep, they're a bit softer. So what means finally for the plant is that it's a bit easier for, if you have mucilage, to extract water from the soil, and also that more water finally is available at the given transpiration rate. So plant will wilt a bit later in that way. However, so this is based on simulation. It's based on some assumptions. And the question is it really true that these rhizosphere property processes that they happen around the single root, do they really play a role at the plant scale? So do gradients in water potential 1 millimeter around the roots, do they matter for the plant? And well, you need to measure it. And what do we need to measure, by the way? So these gradients in water potential, this resolution, these things are changing in a millimeter. So we don't have an instrument that measures gradients in water potential in a millimeter. So the instrument is bigger than the gradient. So it doesn't work. So another way is to measure the difference in water potential, at least, from the soil to the leaf, to the xylem of the plant. That's already something. So you know basically the water potential between the point A and B that I showed you at the beginning. That's the first thing, which is still not easy. And I show you this, but still there are methods to do it. And one, there are not many, there are a few. One was developed by John Pasura, was published already in the 80s. And I showed this, and it's not in many places. So if you want to measure, you have to go there. And I show this picture because this is, so this machine that John Pasura built actually is very close to the lab of Parkour, so the speaker before. So that region is a pretty important region, you can see it this way. And so how does it work, the machine? So it's very simple. So you have it here. So you have a pressure chamber. It's similar to a Scholander bomb where you grow the plants, but the plant is intact. The plant is above, is a cuvette where you can control transpiration. You can control humidity. You may impose higher light or lower light. And the idea is that you're applying a pressure in the soil down there. The pressure is transferred to the root system. And when you increase the pressure, at the point, you find that the cut leaf here, it starts to exuding water. Now, you know that at that point, the water here is at atmospheric pressure. So the definition of water potential that I told you at the beginning, the work that you need to do to get the water out of the soil. That's how the way you're measuring. So the work that the plant has to do to bring the water there. You also have an osmotic component that we are not measuring here. This is we have to accept. But the principle is that the pressure that you need to apply to bring this drop of water there at atmospheric pressure is equal to the suction that there would have been in the xylem if you were not applying that pressure. So you're measuring the suction in the plant, the tension in the plant. When the plant is transpiring, when the plant is start to be exposed to drying soil, the plant is exposed to high transpiration rates. And you can play with it and measure. So that's the first thing. The second thing is, okay, we can measure the difference in water potential between soil and plant. The second thing is, how do we know that rhizosphere processes may affect this gradient, this difference in water potential between the soil and the plant? So when I was there, I was lucky. There was a scientist, Manny Deleuze, and he told me, look, I have two mutants. I have barley with and without hairs. They have the same root architecture, leaf area, plant. They look the same. The only thing is that they lack root hairs. So we have two mutants, one without hairs and one with root hairs. And you see also because of this formation of rhizoshift. And we tested, we put them in the machine, and we tested if the plants were performing different. And having root hairs, which is something that happens all in the rhizosphere, so something in the millimeter scale is going to affect all the plant-soil water relation. And if you look in the literature, you find everything. So you find review articles on root hairs where they say root hairs are important for water and nutrient uptake. Left like that. You have others, they say root hairs are important only for nutrients, for water doesn't matter because water is very mobile. All accepted, not critically. So I think we don't know. I don't know I don't know any definitive experiments showing that. They're contradicting results. And so how should they work? Why root hairs should help? Well, the hypothesis is this one. So if you have root hairs, which can also extract water from the soil, for a given transpiration rate, the consequence is that you average the fluxes over a larger surface. So if you don't have root hairs instead, the velocity, the flow velocity at the root surface, it gets big. And remember that the gradients in water potential, they're related to the flow velocity. So the second thing is that root hairs, they have an advantage compared to the soil, is that they don't have this problem of the radial geometry. So you can imagine this is the root hairs, this is the soil, and you can see as a flow in parallel. In a flowing parallel, water flows where it's easier to flow. So in a wet soil, water will flow here. No way that it has to go to this point. But if this part is getting dry, and then you have additionally the problem of these radial gradients, water will start to flow on this part. And here, since the root density increases close to the root, actually you don't have that problem. Flow velocity is constant. And so finally, what you can expect is that the gradients in water potential, if you have root hairs, they look something like that. So if you don't have root hairs, you get very steep gradients around the roots, particularly at high transpiration rates. And if you have root hairs, the gradients, they're the same until this point, and then they get a bit smooth. So we're still hypothesizing. What did we measure, and what did we find out? So these are the experimental results. So I just show one case. This was a sandy loam, was pretty wet. It was water content of 17%. And we imposed during one day, we imposed the cycle of increasing transpiration. We started in the morning. You can increase it stepwise. You get a peak in transpiration, and then you decrease transpiration. So you kind of reproduce morning, midday, and then evening. And in the lower figure, you measure the balancing pressure. So the suction that you have in the xylem to sustain that transpiration demand. The red line is with hairs, and the blue line is without hairs. And what you find is that initially, when the transpiration rate is low, it doesn't matter. Root hairs, they are not really relevant. But when you reach this point, high transpiration, you see that a very rapid increase in the tension in the xylem. And it's a lot. You may lose 1 megapascal in 20 minutes. So this is fast. And and then you decrease transpiration, and these gradients, they partly relax. So I like to plot this relation. So you measure pressure and transpiration over time, and it's nice to plot the relation between the tension in the xylem and the transpiration. This is what you get in this figure, and you get these interesting loops. So in a wet soil, these lines are straight line. You go up linear, you go down linear. If you are this is still wet, but if you get to high transpiration, when you approach, here you are the same. Without hairs, doesn't matter. When you approach this point, the water potential starts to shoot up without hairs, and this doesn't happen if you have hairs. Interestingly, even if transpiration is reduced, so even when stomata will close, this water loss, this 1 megapascal that you lost, you don't recover it that rapidly. So if the soil fails, you're going to pay it for 1-2 hours during the day. So basically, that's all. So that's what I wanted to show you about the results. The explanation is that the slope of this curve is the conductivity of the roots, while what you're losing, so how much you deviate from the straight line, actually, this delta P is equal to the gradients that you lose around the roots. And since all what we changed in this plant is the root hairs, it means that very likely this difference, this water loss, actually, they really happen in the rhizosphere. So we need to look at that point. So I come to the conclusion. So a large drop in leaf water potential occurs at high transpiration rates, even in wet soil. And this you measure this. And what I found out based on these things is that these gradients, this potential loss, this tension, actually is due to big gradients in a very tiny region of soil around the roots. And this means that small scale and fast processes, they are important for understanding the tension that you have in the xylem. And I see mucilage and root hairs as kind of traits that enable to sustain high fluxes, and I see them rather like a safety mechanism in case of drying soil and high perspiration rate. So when you have very stressed events, these things, they may help the plant to stay turgid, to stay cool, to keep transpiring for some time. Okay.
Thank you very much, Andrea, for sharing very valuable information on soil, plant, water, and